Now, about our locus of conic sections, if you remember from the extension, from the 2-unit course, we did the locus of a parabola. So we showed that it's equidistant from a point and a line. So we're able to find that locus by doing our spanning out, completing the squares, and getting it back to that form. So that was all well and good. Same with the circle. We were able to use our distance formula, be able to work out the formula because it's always 2 units from from a point. So we're able to find our equation there. That was all good as well. What about this one? A point moves such as half the distance from the point 1, 2 compared to the distance from the line y is equal to -3. So when we start that and draw it up, and we get a point PA, so if we use our distance formula, half of a distance of PB, so this would be PB up there, not on the bottom, and then the distance from P to B would be y plus 3. Calculate it out, and you get this. Now, believe that or not, that's an ellipse. It's not an ellipse will come up against a lot. But basically what's this showing is that the distance from a point is half the distance to the line. As we said before, the eccentricity of an ellipse is a fraction. Okay, it's close to every point on the curve is closer to the focus than it is the directrix. So we have that where the parabola was 1 to 1, circle, there's no eccentricity. But this is what we get. We won't get these ones because we're only dealing with, if you looked at the syllabus notes, we only deal with the one where the center is at this origin. So we don't have to really worry too much about that one. What we do have to worry about is our parametric representation. Now, we're looking at parametric representations in extension 1 as well. So what we want to be able to do is find the parametric representation of the ellipse. In the extension 1, we're doing the parabola. In 2-unit, we looked at the circle. So how do we do this? Well, if we've got an ellipse, now our ellipse was drawn there, we draw what we call the auxiliary circle. Now, the auxiliary circle has the radius of the major axis. And so we've got that circle sitting there. We've got the point on the circle. If we've got a point N here, which is 0, 0, it wouldn't be sitting there. It'd be a sine 0 up there. So it wouldn't be sitting on the circle there. So it's being pushed around. But our Q value there would be a cos theta, a sine theta, where this one here is a cos theta, b sine theta, because we're relating it to, it's related to b. So we have that. So how does this help us? Well, what we can do is start to play around. Because we know the coordinates of Q are those, the coordinates of P are those, we take our coordinates of P and sub them in. So we get a squared on x squared on a squared, y squared on b squared. Well, we know that's the equation of the ellipse. So we substitute a cos theta in. And what do we work out? Well, we get a squared cos squared theta plus a squared y squared on b squared equals 1. So y squared on b squared is equal to 1 minus cos squared theta because the a squareds cancel. Y squared would equal sine squared theta, or y would be squared sine squared theta. Y is equal to b sine theta. So this is where that's going to come from. So if you're looking here going, well, how do we get that? Well, the idea is that from the auxiliary circle, we know the point across here should be a cos theta. So the point there is a cos theta. We know that because that's a distance of a, so we know we can get theta. That's a cos theta. The distance up there was a sine theta. Really didn't make much difference. But we know that if a cos theta gets substituted into the equation of that ellipse, we're going to get y being equal to b sine theta. So that's where the coordinates start to come from, because we know what the x coordinate is, and we can sub that in because that's the same x coordinate because that's all in line. So all in line there. So we know the x-coordinate, sub it into the equation of the ellipse, and we get the y-coordinate there. So there's our parametric values. What else can we do? We can find tangents and normals to the ellipse. And to do this, we'll use implicit differentiation like we did in the extension, the graphs topic. So getting the implicit differentiation and getting dy dx, because we're going to find a tangent, we need a gradient. So we get our gradient function. So have a look at that manipulation. I won't go through it all with you. You can read it through and check how we get minus b squared x on a squared y. It's just manipulating all the algebra after doing the implicit differentiation. So the gradient there, it would be pick a point on the ellipse, say x1, y1. Well, sub those values in. There's our gradient. The tangent is going to be y minus the y1 equals a gradient outside of x minus x1. Expand it out. Now, there's going to be a little bit of manipulation to do. Now, we get to this point here. So we've expanded it out. We've collected terms across here. So we can, then if we go, okay, let's divide every term by a squared and b squared. So we get this situation. X times x1 on a squared, y times y1 on b squared is equal to x1 all squared on a squared plus y squared, y1 all squared on b squared. Now, if we look at that part, x1, y1's a point on the ellipse. And the equation of the ellipse is x squared on a squared plus y squared on b squared equals to 1. So if that's a point on the ellipse and it's putting into the equation of the ellipse, that must all equal 1. Because any point on the ellipse, when we substitute in the equation, must come down to being exactly equal to 1. So that's where we were able to write that there. Now notice, this is a straight line because it's just x and y. X1, y1, a squared, b squared are just numbers, and it's all equal to 1. There's your equation of your tangent. So we need to be able to determine that when we have some numbers thrown in there. So again, have a look at the algebra, see if there's any problems. But there's our little trick: divide by a squared, b squared, and be able to realize that that can come down to 1 because it's just satisfying the equation of the ellipse. Doing the gradient of the normal, well, take your negative reciprocal, substitute it in, and then you're able to manipulate as we go through. So put your equation, your normal in, y1, x1, y1 with the gradient, multiply through, and then we divide by x1, y1. So we're able to do some divisions and get our great equation of the normal as we've got it there. The tangent of the normal in terms of our parametric equations. Again, I've gone right through and done this. You could basically, because you know they're the values, you could just take those and substitute it into what we did before, and that would work. That's fine. But doing it through finding the gradient of the tangent, well, we knew what the gradient of the tangent gave us before, and if x1 and y1 are a cos theta and b sin theta, we're just subbing it in there. And then we're subbing it into equation of the tangent and then manipulating. Remember, and you can see this here where you get ab sine squared theta plus ab cos squared theta. Well, that would be ab outside of sine squared theta plus cos squared theta, which is equal to 1, which is able to come down and be able to put it into the divide and get it all equal to 1 on that side. So there's our manipulation there. Again, have a look at the gradient, the algebraic manipulation there, but it's coming back from the gradient of the tangent and just the equation of the straight line. And the same thing happens with the gradient of normal as we did before. We substitute those in to get it back to this form, which is the standard form for the gradient of the normal. We're just dividing by the sine theta cos theta once we manipulate it all, and getting a squared minus b squared. So there's how we find and do the algebraic manipulation to get the gradient and tangent. We'll get the gradients and then the equations of the tangents and normals in both Cartesian and parametric forms. So looking at some questions here. if we put this information from what we've got here, A is the point A cos alpha B sine theta. So alpha. So there's the point A. And it lies on the ellipse. B is the foot of the perpendicular from A. So it comes down and forms a perpendicular. And the normal at A cuts the x-axis at C. So we've got a tangent, we've got a normal. So there's what our diagram looks like. Derive the equation of normal AC. Well, how do we do that? Well, as we did before. We get our gradient of our tangent. We've put it in parametric form. So our gradient of our normal would be in parametric form. And then we're able to do our substitution in the equation of the straight line, expand out, collect our terms, divide by the sine theta, sine alpha, cos alpha in this case, to get that form. So again, pretty much what we've done in all the other courses, except this time it's a little bit harder manipulation when using implicit differentiation. Show the length of CB is B squared cos alpha on A. So what's the coordinates of B? Well, they would be A cos alpha 0 because that's the foot of the perpendicular. Go back and check your diagram. At C, we know that y is equal to 0. So because it's along the axis. So therefore we could say, well, we get AX on cos alpha plus 0 because we were able to get it from our equation there before. And we've got that B equal to A squared plus B minus B squared. Rearrange that to get XB cos alpha on A with an outside of an A squared minus B squared. So we've just taken and did the division by cos alpha on A. Sorry, A on cos alpha. So the equation, the distance there, we're not too sure exactly whether on the positive or negative, so we'll take the absolute value because we want a length. So we get the distance there of the CB, the value of the coordinate C on the x-axis minus the coordinate B on the x-axis. And we do our manipulations, we expand it out, and we get the A cos alpha cancelling, we get B squared cos alpha on A. So that's how we get that. We just found our coordinates of B and C and took the absolute value because we didn't know whether it was there, or B's inside C or outside of C. We weren't too sure. We weren't too worried. If we want to find the length, it's an absolute value. So question 2 there. Show the tangent to the ellipse at the point has that equation. So again, this is pretty standard. We're finding out, doing our derivative, getting our gradient of the tangent in parametric form, and then getting our equation of our tangent like we've done before. Check the algebra. Make sure you can able to do that in the parametric form. And then we're told the ellipse meets the y-axis at C and D. Tangents drawn at C and D on the ellipse meet the tangent in A at the points E and F, respectively. Prove that we get that result. Okay, drawing it up. There's our tangents at where the ellipse meets the y-axis. There's our tangent we got from part A. So there's the equation of the tangent there. So we know it meets that at the point A cos theta, B sine theta. So what we need to do is find the points where at E and F where it cuts those. So at E, what do we know? We know y is equal to B. So we're able to put that in the equation of the tangent from A. So we're able to put y is equal to B, find the x value, which would be A cos theta outside of 1 minus sine theta. So check the manipulation, and that would be the distance CE, because C's 0, and we're going to that value there, so that would be distance of CE. We can also do the same. At F, we know y is equal to B, so substitute minus B in, and we're able to manipulate this down to the x coordinate, which would be A cos theta outside of 1 plus sine theta, which is the distance df. So we're told, take CE, multiply it by df, show that it's equal to A squared. Well, let's do that. We get A cos theta 1 plus sine theta, A cos theta 1 plus sine theta. Well, that would give us an A squared cos squared theta. And we've got the difference of two squares, 1 minus sine squared theta, which is cos squared theta. They cancel, gives us A squared. So there's our manipulation. So we've used our ideas of finding equations of tangents, subbing in values to get distances there that are not very pretty, but then might be able to multiply those and come down to the value of a squared. So we've been able to solve that problem as we've gone through. And that's some of the manipulations you're going to see as we go through. So what we need you to do is be sure about how to find the gradient of using the implicit differentiation, then being able to find the tangents and normals in both Cartesian and parametric forms. So have a practice of those, have a look at again at the video probably if you're not too sure, and be ready to have a go at some of these types of problems where we need to get our tangents and then apply some other type of understanding and manipulation towards solving a problem.